2026 USA JMO problem number 1. So let a and b and c be distinct positive integers such that ab plus c equals c squared. Prove that a minus b squared is equal to 4c. Okay, so we have a and b and c are distinct, and they're all positive integers, so they're all positive integers. And this equation must hold true. And so originally we can probably try to do something, probably won't work, but it's always worth a try to just do things and see how they work out. And so I'm thinking ab equals c squared minus c. So we can just go a squared minus 2c squared plus 2c plus b squared greater than or equal to 4c. Get a squared plus b squared greater than or equal to 2c squared plus 2c. And it's not immediately clear where we go from here, so I guess that didn't really lead to anything useful. And so I guess a big rule of thumb for these sorts of USA JMO and USAJMO problems and even AMY problems is just to play around and see what happens. And so if things fail like this, we try again. And the next thing I'm thinking is that we have positive integers, and so an inequality. And so why don't we try using our own inequality? How about the AM-GM inequality? And, I think naively just going a plus b plus c over this isn't really going to lead to anything. Even we could probably plug this in, but I don't think we're going to get anything out of this because we want an a minus b term. And there's not really an obvious way to get an a minus b term on either side of this, so maybe this isn't the right approach either. So back to thinking. One possible idea is we could try to force an a minus b term somehow through some sort of other equation. And what I'm thinking is, since we have this ab term and we also want an a minus b term here, we could do Simon's favorite factoring trick, but a little bit modified. We could do like a minus 1 b plus 1 equals ab. So that's this term, and we can plug this in now. ab minus b plus a plus 1. Or since we'll flip these signs so we can get a nice a minus b. So it's going to be a plus 1, b minus 1. And so then we'd get, oh, I wrote the same signs again. A minus 1, b plus 1. So then we'd get plus a minus b minus 1 at the end. So we have this, and now we can plug in the ab equals c squared minus c thing. So we get c squared minus c plus a minus b minus 1. And it's not really obvious what we do with this. I mean, we can, like isolate this a minus b term. And then we'd get plus c squared minus c minus 1 here. But we want to have something on this other side. We want to make an inequality at the end of the day. And so one inequality that comes to mind is that this is all greater than or equal to 0. And I'm making this claim because a and b are also positive integers. The lowest a can be is 1, and the only way we could ever get this side to be 0 is if a equals 1. So maybe that's something useful to keep in mind. So that's the only way equality happens, is if a equals 1. And for all other positive integers a, we get that this term is always going to be positive, and so always greater than 0. And so now we have an inequality with a minus b term, and we have a c in it, and it's also an inequality. So let's just write this down and start doing stuff. Get a minus b plus c squared minus c minus 1 greater than or equal to 0. A minus b greater than or equal to c squared minus c minus 1. And then square both sides. A minus b squared greater than or equal to c to the 4th minus 2c cubed minus c squared plus 2c plus 1. Yeah, minus c squared plus 2c plus 1. And so, or is that minus? Okay, no, this is good. So we get this equation. And so now we have this, and we basically want to prove that a minus b squared is greater than or equal to 4c. If we prove that this is greater than or equal to 4c, we basically have solved the problem, because if this is greater than or equal to 4c, then this a minus b is definitely going to be greater than or equal to 4c. So we want to prove c to the fourth minus 2c cubed minus c squared plus 2c minus 1 greater than or equal to 4c. And so we want to prove c to the fourth minus 2c cubed minus c squared minus 2c minus 1 greater than or equal to 0. And so that's basically just finding the roots of this equation, which we can use rational root theorem here. We could either like -1 or +1, and +1 definitely does not work here. So maybe -1 is a root. We can get 1, and this is again positive, and yeah, I don't think -1 is a root either. So looks like there's not clean roots here, and maybe there's a way to factorize into fractions, but that wouldn't be useful either since we're dealing with real numbers. So let's just try to see which numbers this holds true for, because if this holds true for all like c's greater than something, then at least we have a partial result, and that's better than a nothing result. So let's try to see. We know it's not true for 1 because we get 1 minus 2 minus 1 minus 1 minus 1, and that's definitely not going to be true. And then, or this is supposed to be a +1, I think. Yeah, this is supposed to be a +1 because that was supposed to be a plus and that's supposed to be the 1. Okay, and so even with the +1, it's still not going to work. Let's try, so c does not equal 1. So let's try c equals 2. Does that work? We get 16 minus 16 minus 4 minus 4. Yes, c does not equal 2 because c equals 2 doesn't work either. C equals 3. Does that work? 81 minus 54 minus 9 minus 6 plus 1. And 82, we get minus 68, and that does work. So c greater than or equal to 3 is going to work. So we found basically so far that this equation, or this expression, a minus b squared is greater than or equal to 4c for all c greater than or equal to 3. And so this leaves us with the cases of c equals 2, what happens, and c equals 1, what happens. And so since we couldn't prove that this equation holds true, let's just try to prove that this thing holds true. And for c equals 2, that means that it's going to have to be greater than or equal to 8. And the way we do that, we need to get a and b that satisfy this. And again, we have to have the ab plus c, or is it ab plus c? Yeah, ab plus c equals c squared. So given c equals 2, we get ab plus 2 equals 4, and there we have a contradiction because then ab equals 2. And so that means either a equals 1 or a equals 2 or b equals 2. And if either a equals 2 or b equals 2, then we can't work out because then either one of these is going to be equal to c, which is also equal to 2. And so they're not distinct. And so we have no possible solutions or no possible triplets a, b, c, or a, b, 2, where c is 2, that satisfy this equation. So there's really no solutions there. And so I'm assuming that there's not going to be any solutions for c equals 1 either. So we get ab plus 1 equals 1, ab equals 0. And so for a and b are both greater than 0, this has no solution. So we found that for c equals 2, there's no solution. C equals 1, there's no solution. And so for all c's greater than 3, we have our equality or inequality holds. So we've basically proven this is going to be true for all c greater than 3. There's no possible solutions for c equals 2 or c equals 1. And so we're almost done. In order to be fully done, we'd basically have to write this whole proof backwards and have an actual proof instead of this all scratch work. We'd have to formally write up our proof. So we'd have to prove this equation, and then we'd have to work backwards to get into this one, and then work backwards and so on and so forth until we have a formal proof. But for our purposes, right now, we are done.